So these are lecture notes for section 11.4 on probability. So what is probability? So in general, probability is the study of random phenomena. So things that don't have a way to determine, with certainty what the outcome is. And so we can measure probability on the scale from 0 to 1 or 0% to 100%. And so events that are impossible to happen have a probability of 0, and then the events that are certain to happen have the probability of 1, and then the rest of the phenomena, the rest of the events sort of range between 0 and 1. And so the closer the probability gets to 1, the more likely the particular event is to happen. All right. So essentially, the question that we're going to be asking when we deal with problems of probability is, what is the likelihood of an event happening? So what is the likelihood an event will occur? So the key truth about random phenomena that's used in the study of probability is the fact that random phenomena, so anything that has uncertain outcome, so random phenomena are characterized by having a short-term unpredictability. So that means on a short-term basis, you don't not really know what the outcome is going to be. But these random phenomena have long-term regularity. So what does that mean? So let's say if we take a tossing of the coin, which is a random phenomenon, because if you toss a coin, there's no way of knowing, as long as it's a fair coin, there's no way of knowing which side it's going to land on, whether it's going to land on heads or tails. And so while short term, meaning with every toss, we don't really have a way to predict what the outcome is going to be. However, if we toss the coin many, many times, so in other words, looking at kind of a long-term pattern or behavior, we'll see that the heads come up 50% of the times and the tails come up 50% of the time. So there's that long-term regularity in the outcomes, while short-term, there's no way to predict what the outcome is going to be, whether heads or tails. And so that's what we're going to do when we put a probability number on any event. We're really just characterizing that long-term regularity. If we were to repeat the event many, many, many times, what is there going to be some kind of a pattern, some kind of regularity in the outcome? So that's what the probability value tells us, that regularity value. All right, so let's look at some of the definitions in this section. So basically, a couple of words or terminology that we're going to use is, so the first term is experiment. So experiment is just any occurrence with uncertain outcome. So anything like tossing a coin or rolling a six-sided die, anything that you do that you don't know how it's going to, what the outcome is going to be, we can call that an experiment. Now, another term called the sample space. So sample space is a set, so this curly bracket notation should remind you of the set theory topic that we looked at in the beginning of the semester. So sample space is a set of all possible outcomes. So if we look at an experiment, if we look at all the different ways, all the different outcomes that can happen, and we list them as a set, we can call that the sample space. So again, if we're looking at the rolling a six-sided die, we've got 6 different outcomes. So either it's going to come up as 1, 2, 3, 4, 5, or 6. So 6 sides, 6 possible outcomes. If we list them all, that's going to give us the sample space. All right. Another term we have is called the event. And so event is just any subset of the sample space. So let's say if I'm interested in the event such as rolling an even number, so that means either rolling a 2, a 4, or a 6. So a subset of the sample space is called the event. And then the outcomes that are favorable, in terms of the favorable for the event are basically the outcomes that make the event happen, and the unfavorable outcomes are the outcomes that if the event does not happen. So in other words, the outcome 2, 4, and 6 are favorable to the event of rolling an even number, but if you get outcome of 1, 3, and 6, these outcomes are unfavorable for the event of rolling an even number, because obviously 1, 3, and 5 are odd and not even. Alright, and then generally to compute the probability, it's a relatively simple procedure. What you have to do is just count all the number of outcomes in which the event can happen. So again, if we're interested in finding the probability of rolling an even number, well, there's, again, 3 outcomes in which that event can occur. And then all we have to do is just set up a ratio of that number of outcomes out of the total number of outcomes, which is, of course, the sample space. So in this particular example, the number of outcomes in the event, so if we're looking at the event of rolling an even number, let me write this over here. There's 3 outcomes in that event, 2, 4, or 6, so 3 total outcomes, and the sample space has the size of 6 because there's 6 total outcomes, and so the probability of rolling an even number is a half. And anytime we set up a probability fraction, a probability ratio, we got to make sure to reduce our fraction. So in reduced form, the probability of rolling an even number is a half, so 1 out of 2 or 3 out of 6. Right. Okay. All right. So let's look at basically, the rest of the slides in this section. Just look at various contexts in which we can compute the probability. All right. So let's look at the first context. We'll just continue looking at the context of rolling a 6-sided die. All right, so that's our experiment. And so each particular problem that we have here is an individual event. And so we're going to be computing the probability for each of those events. Okay. So the first event is rolling a 5. Okay. So again, to find the probability, we have to count the number of ways in which 5 can occur. Well, there's only one outcome of 5, so one outcome out of the sample space total, which is 6. And so really, because all of these events deal with rolling a 6-sided die, for each of those fractions, I already know that the denominator is going to be 6, because the sample space is 6 for this particular experiment of rolling a 6-sided die. Okay. All right, so let's keep going. So the next event that we have is, so it's the same event that we just looked at, rolling an even number. And we already said that we have 3 ways to get an even number. That is to get either a 2, 4, or 6. So that's 3 outcomes for an even number. And out of 6 gives us a half. Let me move this guy over. All right. The next event that we have is getting a value that's less than 5. So let's see how many outcomes that are less than 5. Well, we've got 4, a 3, a 2, and a 1. So that's 4 total outcomes. Out of 6 reduces to 2/3. Next one, next event is getting a number that's less than 15. Well, every outcome here is less than 15 because 6 and down are all less than 15. So that's 6 out of 6. So notice the probability of that event is 1, meaning you will always get a number less than 15 because every outcome is less than 15. So that event is certain to happen. So remember, the probability of 1 tells you that the event is certain to occur. Okay? And then the last event is getting an outcome that's greater than 12. Well, the highest outcome that we have is 6. And so therefore, there are no outcomes that are greater than 12. And so the probability of that event is 0, because 0 divided by 6 is 0. And so if I were to put a label on that, so this event is impossible, while this event is certain to happen. All right. Okay, so it's a little summary of that. Basically, events that are certain to occur are assigned a probability of 1 or 100%, and events that cannot occur assigned probability of 0, and so everything else, every other probability value just ranges between 0 and 1. Alright, let's look at another context. Another popular context for finding the probability is drawing a card from a deck of cards. So we're looking at a deck of 52 cards, and very important to note here that we're drawing just one card out of that deck. And so just for reference, I'm giving you, showing you the picture of the deck here. Alright, and so in case you're not familiar, and your reference sheet will also contain this photo of the deck of cards, and kind of tells you the different types of the cards. Alright, so this just kind of remind, or maybe just look at the deck as a whole. So again, we know that there's a total of 52 cards in the deck. Another thing that you'll need to know sorry, is that every suit, so like heart, clubs, diamonds, and spades, there's 13 cards of every suit. And then of course, in terms of the what do you call, the types of a card, like the ace or the 2 or the 3, there's four of each type. Alright. Alright. So again, we're finding the probability of drawing a card from this deck, and so because there are 52 cards, we know that the sample space, or the total possible outcomes, there are 52 of them for every event that we're going to look at. So I can already write that down. So I know there's 52 total cards. So the first event that we want to look at is drawing a diamond. Oh, let me move this. Can I move it up? No, I cannot move it up. Okay. So drawing a diamond. Alright. So I know there's 52 cards. How many diamonds are there? So again, you can count the diamonds, but if you do, there are going to be 13 of them. And then that fraction can be reduced. So notice it's just one group out of 4, so it actually can be reduced to 1/4. So your probability of getting a diamond is 1 out of 4 chances. Alright, the next event is drawing a picture card. So once again, I know that there's going to be 52 cards total, so that's my denominator. So how many picture cards are there? So I've got 4 jacks, 4 queens, and 4 kings. So that's a total of 12 cards. Alright, again, we can reduce this, and most of your calculators, your scientific calculators, will give you a function, will have a way for you to reduce fractions. So I can demonstrate that in class, but I see both 12 and 52 are divisible by 4, so 12 divided by 4 is 3, 52 divided by 4 is 13. So reduced, getting a picture card has a probability of 3 out of 13. Alright. So let's go down. Alright, the next event is getting a queen of hearts. So let's see, how many queens of hearts are there? Well, there's only one. There's only one queen of hearts. So that's your chance of getting that card is 1 out of the whole deck, which is 52. So 1 out of 52. All right, and then the last example, what is your chance of getting a card that's a heart and a diamond? So this is kind of a trick question, but the key thing to remember is that you are only taking one card out of the deck. So there's not a single card in the deck, goodness, that's both a heart and a diamond, because you have single hearts or single diamonds, but you do not have a single card, any one card that's both. And so your chance of getting that card is 0 out of 52, or just 0. So there are no cards like that. And again, the tricky part is that we're only picking one card, and a single card cannot be both. Okay, so let's move on. Alright, so this is one of the questions that I'd like for you to answer as part of just letting me know that you're watching this video. So I'd like for you to respond to this question. So which event would you rather bet on? Would you rather bet on rolling a 6-sided die and getting a 3? Or would you rather put your money on drawing a king from a 52 card deck? So which of these two events would you bet money on? Obviously, well, just let me know, and let me know how you made your choice. Alright, there's going to be another question that I'll ask closer to the end of this video, so keep watching. Alright, so another context that we have is tossing a coin. Again, another common context for calculating probability. Alright, so let's look at that example. And so in this case, actually, we are tossing 2 coins. Alright, so remember, every probability calculation, you do need to know your sample space, meaning what are the total possible outcomes for the particular experiment. And so in this case, because we're throwing the coin twice, you've got 4 different possible outcomes. So you might get a head and a head, so the first toss and the second toss. You might get a head and then a tail, so head on the first toss, tail on the second, or a tail in the head, or tail and a tail. So those are your 4, so the sample space, essentially, the sample space is 4, right? It has a size of 4. That's which is, because 4 is not in the sample space, but sample space has a size of 4. So anyway, so our denominator for every event here is going to be 4. And now we have to look at the outcomes in which we can get the particular event. So the first event that we're finding probability for is, what's the chance of getting 2 tails? Well, you only have one way to get 2 tails, and that is if you get a tail and a tail. So that's 1 outcome out of the total of 4. So the probability of that is 1 out of 4. The next event is finding the probability of getting a different outcome on each toss. So you got 2 ways to get that, and that is if you get a head and a tail, or a tail and a head. So there's 2 ways to get that event out of 4. So that's a half. And then the last question is, what is the chance of getting at least 1 head? So we've kind of been exposed to this word at least. So at least 1 head means of getting 1 head or more. And so here's we're getting a head, here's we're getting a head, and here we're getting at least 1 head, we're getting 2 heads. So for the total probability of 3 out of 4. Okay. Right, next. Alright, so sort of a similar context, and again, I'm already giving you the sample space, the size of the sample space. So here we're looking at a family with 3 children. And so the resulting space is the following. So taking into account the birth order of the children, you might have the oldest, middle, and the youngest kid being all male, or maybe the oldest, middle being male, but the youngest is female, and so on. So we're taking into account the birth order of the children and the different genders of the children. And so this right here lists all the possibilities, all the possible outcomes. And if we count, the size of the sample space is 8. So there's eight different possibilities. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So that means 8 is going to be our denominator for every event here that we're going to be finding probability for. So the first event that we're interested in is figuring out, if I were to randomly pick a family with 3 kids, what's the chance of getting a family with at least 1 female child? So again, at least 1 means 1 or more. So let's see. So here we have a female. Here we have 2. That's 1 or more. That's 1. That's 1 or more. 1 or more. And this is 3. So that's every family except for the 1 family with all male children. So your chance of getting at least 1 female child, a family with at least 1 female child, is 7 out of 8. So it's every outcome except for 1. Okay, the next event is picking a family with exactly 2 female children. So now we don't want to count 1 or more. We're looking for exactly 2 females. So here's a family with exactly 2 females. Here's a family with exactly 2 females, and here's a family with exactly 2 females. So there's 3 different possible families out of 8. Okay. All right. All right. Now, so far, the examples that we've looked at, we can, the particular experiments, or the kind of phenomena that we'll be looking at, we can clearly define the sample space. We can clearly define all the possible outcomes. Now, not all events are like that. So far, what we've been working with is computing the theoretical probability. That's when you're able to clearly count the sample space. However, a lot of the events out in the real world, you can't really account for the total possible outcomes. And so another way of estimating probability is to collect data, so use statistics essentially. And so we don't have to know this law, but essentially what this law says is that if you have an event that's, it's not very simple. It's not as simple as tossing a coin or rolling a die. So like when you roll a die, you can clearly see all the possible outcomes, but there are certainly events out there that you don't really know what all the possible outcomes might be. However, if you repeat this experiment many times, you can approximate the theoretical probability by counting the number of times the event occurs out of the total, the sample of the data. So basically the sample space, or the size of the sample that you've collected. Okay, let's look at an example. All right. So here's our example. So here, what we did was, let's say we collected data about, so it's the survey data regarding color blindness. And so the data, let me kind of tell you a little bit about this chart. So this chart, this kind of data chart, will always tell you the total number of people that were surveyed. So this number right here is basically becomes our sample space. So that's going to be the denominator for every computation that we do in this case. Okay. And then this data has been divided into categories. So we know that out of those 1,000 people, we had 535 that were female, and we have 465 that were male. And then within those female, 535, that sort of subset was divided into two other categories of the females that were colorblind and those that were not colorblind. So we had 5 that were colorblind and 530 were not colorblind, and same thing within the male subsample. 45 were colorblind and 420 were not. And then the table also tells you the total number of colorblind people, regardless of whether they were male or female, and the total number of non-colorblind people. All right. So, okay. So now let's see how we can answer some empirical probability questions within this context. All right. So the first question asks, find the probability that if you were to randomly select a person from this sample of 1,000 people, that this person is going to be female. Well, all we have to do is just see how many females are there in the sample. And in the sample, there's 535 females. So that's going to be the number of ways in which we can get a female. So we have 535 ways of getting a female out of a total of 1,000 people. And so in this case, you can actually read, the homework problems will tell you to either give your answer as a fraction, as a reduced fraction, or as a decimal. So as a decimal, this answer would be 0.535. So you have over a 50% chance of getting a female from the sample. Now the next question asks, what is your chance, what's the probability of picking somebody who's colorblind, so without concern for their gender. And so colorblind people, we have 50 total colorblind people. So your chance of getting a colorblind person is 50 out of 1,000. So as a decimal, that will be 0.05. All right, and then the last question asks about the probability of getting a colorblind male. So that one is being specific about the gender. And so again, we have 1,000 people total, and colorblind males, we have 45 in the sample. So we have 45 ways of getting a colorblind male. And again, that reduces to 0.045. All right, so this concludes our review of section 11.4. And so another sort of assignment that I'd like for you to complete is start working on your homework for section 11.4. And I would love for you to attempt at least half of the problems, whether correct or wrong, but by the next time we meet, I'm going to review to see who's completed at least half of the homework problems for 11.4 to give you full participation credit. Okay, thank you.